Welcome to the MOOCs course Mechanical Unit Operations. Till now we have seen the mechanical unit operations, equipment used for mechanical unit operations involving only solid systems, something like size reduction, process of size reduction, how to make analysis of size reduction processes, what kind of equipment are available, how they work, how they operate, etc. Those kind of details we have seen. We have also seen some amount of details about the size enlargement, what kind of equipment are available for the size enlargement. Those details we have seen. So, where basically what we have seen till now, we have seen the mechanical unit operations involving only solid interaction or solid systems only. We have not seen any kind of mechanical unit operations where solid fluid systems are involved. So, now we are going to discuss mechanical unit operations, their working principles, their design, etc., involving solid and fluid systems in a few lectures afterwards. So, now we need to start discussing about the mechanical unit operations involving the solid fluid systems, that is where the solids are also interacting with the fluids, or both of them are moving, or only one phase moving, other phase may not be moving, or both phases moving. Those kind of details we have to see. So, what happens, there are several kind of applications. So, we start with some kind of list of the applications, so that to have a kind of a feel why should we go for a mechanical unit operations involving solid fluid systems, not only just solid systems, right. So, for that, before going into those details, those mechanical unit operations, we need to see some fundamental details about the solid fluid systems, or something like a fluid flowing through a number of particles, or fluid and then solid phases are simultaneously moving, and then we may be doing some kind of separations, etc. Those kind of systems are there, right. So, however, having details about the single particle flowing or settling in a kind of fluid, or a fluid flowing along a single solid particle is going to give some kind of information about the physics of the problem, what kind of forces are acting at the solid interface, etc., which can be used in kind of designing of these solid fluid operations, or the mechanical unit operations involving solid fluid systems. So, that is the reason let us start with some basic information about flow past immersed solid objects, rather directly going to the mechanical unit operations where solid fluid systems are involved. Because if you directly go to those mechanical unit operations, we may not able to understand several details, because in order to understand those details, we need to have some kind of fundamental information about the flow past immersed solid objects, single solid object, as well as the flow through packed and fluidized beds, etc. We need to have some kind of a basic information, then only we will be going into the details about mechanical unit operations. So, the title of this lecture is the flow past immersed solid objects. Why solid liquid systems are important? Because solid fluid multiphase flows are very common in process industries or material process industries, chemical industries, polymer industry, food industry, textile industry. Whichever kind of material processing industry if you take, you can find these kind of solid fluid multiphase systems almost a kind of ubiquitous. So, it is a kind of very important to have kind of some information about these systems. So, what are the situations where we have in general these solid fluid systems involving? So, something like flow through packed and fluidized beds. So, where packed beds are sometimes used to kind of heat recovery systems or heat storage systems, right. Fluidized beds are in general used for the kind of coal combustions, etc., or some kind of catalytic reactions, etc. So, for those purposes in general we use. So, where there is a relative motion between solid and fluid systems. We have filtration, etc., operations in mechanical unit operations, where we will be using the principles of flow through packed beds, etc. Then we have several catalytic reactions in general chemical and process industries, wherever these catalytic reactors are there. So, solid catalytic phase is interacting with the surrounding liquid phase, with which it is going to undergo a kind of a reaction process. So, under those conditions also, under those catalytic reactors also, there is a kind of relative flow between solid and fluid phases. Then we have a gravity sedimentation like in clarifiers. Actually several types of gravity sedimentation chambers or equipment are used, which are used for the separation of the particulate phase from a kind of suspension, or in general, or from a kind of sometimes they are also used separating the particles in different fractions. So let us say gravity sedimentation in clarifiers. Clarifiers are in general remove almost all particles. Virtually they remove all particles from fluids, such as in sedimentation tanks, like what we have a kind of tank in which we take the suspension, whichever the suspension having the particles and then fluid together. So you take them in a container or tank like this, and then you allow this particle to settle. So what happens after some time, this entirely this most of this almost all these solids may be settling at the bottom, whereas at this top clear liquid may be forming, whereas all the solid particles may be settling at the particle. So this is known as the kind of sedimentation. It's a kind of batch sedimentation. So we are going to study these details also. Then we have a gravity sedimentation like classifiers. So classifiers, like we have a kind of something like that. One example only I am saying. So we have a container like this, right? So from here the dust laden or particle laden air that comes in here like this. So these particles are having different size distribution, let us say. So whatever the particles having the bigger size, they will be having the higher settling rate. So they try to they will be settling at the front part of this chamber like this, while this gas or the air which is carrying particles while it is flowing inside, when we allow to flow this chamber, so the particles having the bigger size, they will obviously having the larger settling velocity, so they immediately fall here. So particles which are having very small size, they may be taking large time to settle. So their settling velocity may be small, so then they may be settling here, in the other extreme. So in the intermediate medium fraction, maybe you can find out. So here we have a coarse particles, we may be settling faster. Then we have a fine particles which may be settling slowly, and there is a kind of medium fraction which may be settling, or settling velocity may be in between of these two range, and then the particle size distribution also in the same in between of these two ranges, and then clear air may be going out from here depending on the performance of this chamber. Of course, in order to have the complete separation of these particles, the size of this chamber, height, etc., and all those things are going to be important, and one has to involve into the design. So we will be doing those design kind of things as well. So this is one kind of other situation where there is a relative motion between solid and fluid system, and then particles are being separated. So this is the sedimentation tanks are something like a clarifiers which separate the particles, virtually all particles, from the fluid. Classifiers are a kind of equipment which separate the particles into different size fractions, as something like dust settling chambers, etc., as discussed here. So I am just trying to give some examples so that to have a kind of feel why should we go for this solid liquid systems or mechanical unit operations involving solid fluid systems. If you see some more examples, we have a sink and float gravity sedimentation. Let us say you have a kind of a particulate flow which are having two different types of particles. Let us say particle A type, particle B type. So their densities may be in general different, or let us assume that densities are very much different from each other. One may be having the very high density, let us say 2000 kg per meter cube. One may be having something like, let us say, small density, something like 500 kg per meter cube. So then what you can do, you can find out a kind of solution solvent which is having a kind of density in between of these two. So then when you allow these particles to flow along with this fluid whose density is in between the density of these two types of particles, then what happens, the heavier particles or the particles of the higher density may be settling at the bottom, and then lighter particles or the particles whose density is the smaller than the solution whatever we have taken its fluid density, then those particles may be suspending or floating on the top of the liquid. So, this is how you can separate out particulate mixture having different types of particles of different density like this. So, however, in such kind of applications you need to find out what appropriate fluid which is having density in between of these two, so that you can clearly separate. And finding out such kind of fluid having the density in between of these kind of solid densities, the particles having high density and then particles having low density, and then finding out a fluid having the medium density of low and high range is a kind of bit difficult task, right. So, then under such conditions people also use complex fluids, or otherwise such kind of systems can also be separated by using a kind of differential settling method. What is differential settling method? You take this particulate flow material whatever is there, you try to crush it to the uniform size. Let us say you take this galena, that is PBS, and silica SiO2 mixture is there, you take that mixture and then you crush them to uniform size, let us say 1 centimeter approximately all the particles, right. So, now you are not finding a kind of fluid which is having a kind of density in between of these two, so that you can do the sink and flow differential settling method. So, then what you do, you crush them into a kind of uniform size, let us say 1 centimeter, and then you allow this material to settle in a kind of solvent, let us take water, right. Then what will happen, let us, because the particle size now dP is same for both the particles PBS as well as the SiO2 now, but the density of PBS is higher than the SiO2. So, what will happen, the particles though 1 centimeter size only, those particles may be settling faster. So, they will be having higher settling velocity, that is something like 13 foot per second, and they will be settling at the bottom as a kind of almost pure PBS fraction. And then particles which are having the silica particles, though their size is also 1 centimeter, their settling velocity is a bit lower, that is 7 foot per second. So, because of that one, again those particles will also those particles may be settling slower. So, those particles may be forming a kind of layer on these particles, on these PBS particles. So, that is how you can have a kind of this kind of two fractions. So, majority of fractions in the bottom you may be having PBS, and then above it maybe you may be getting a separate fraction of the solids SiO2, like this you can separate. This is what known as the differential settling. So, whereas the sink and flow methods, so what you have, you try to find out a fluid, so that heavier particles may be settling at the particles whose density is higher, they may be settling at the bottom, and then particles whose density is smaller than the fluid, then that will be floating in the top. In between we may be having a kind of fluid. So, this is the sink and float gravity sedimentation process, and in bottom one this is a kind of differential settling process. So, these are the kind of some kind of applications we in general see. Okay. So, now we have a centrifugal separation processes also, where in general we try to dry the solids and crystals. We also have the cyclone separators, in general from the process industries, whatever the dust laden fluid, dust laden particles are there, they in general taken into a kind of a cyclone separator, where these particles are being separated and then collected as a particle mass, and then clear air is taken out here. Dust plus air. So, these particles are taken in the cyclone separators, and then in the cyclone separator process the sedimentation, gravity sedimentation is taking place, and then there will be also a kind of centrifugal forces also acting on this So, cyclone separators, here in the cyclone separator we take the dust plus air or whatever the dust laden air is there, that we take here. So, in this sedimentation, in these cyclone separators, particles will be settling and then almost clear air is taken out. So, this is the purpose of using cyclone separator, so that not to contaminate the surrounding environmental air with this dust particles. So, before leaving this dust laden fluid from the industrial gases effluent, so they have to be cleaned like this. Then there is also flotation process, right. Like this, if we keep on listing, there are n number of applications where we can see a kind of relative motion between a solid and fluid systems, and then there may not be occurring any kind of chemical changes. There may be occurring only mechanical changes, mechanical or physical changes occurring, and then so those mechanical unit operations where the solid fluid systems are involved. So, one has to study some details, some design process, working principles, equipment, etc. one has to study. So, that is what we are going to do in the second half of this course. So, however, before going into those mechanical unit operations, let us start with some kind of basics. So, now we understand that the relative flow between solid and fluid or both solid and fluid moving is a kind of very common in kind of process industries, having seen several kind of applications till now. But in such solid fluids flow systems in general, there may be several parameters involved. So, drag is one of the most important parameters. So, this drag is going to be very much useful in the designing of these mechanical unit operations or tuning the operating conditions of already existing design, right. So, either of the conditions, so this drag is going to have a kind of very influential role. So, let us say in this unit operations, along with this motion, there is a heat transfer is also taking place. So, under such conditions, there is a kind of necessity of having information about the Nusselt number as well. If there is a mass transfer in this solid fluid system, then along with this drag, there will also be need for a kind of Sherwood number. So, that is the reason we might have studied several types of correlation for Nusselt number and Sherwood number in our heat transfer courses, right. So, you might have also seen some kind of correlations for the drag coefficients. So, now what we do in this course, we take system where only momentum transport is occurring or only there is a flow phenomena is existing, there is no heat transfer or mass transfer. So, that is the reason we will be discussing about the drag only. So, before going into the drag details, for the individual problems, we need to have some kind of basic information about this drag, what it is drag. So, since understanding this drag is going to be very much influential parameter for the design of a given mechanical unit operation or the multi-phase equipment where the solid fluid systems are interacting, or tuning the operating parameters of such kind already existing design, this drag is going to be very important. So, we need to understand some details about this drag. What is the drag? It is the force in the direction of flow exerted by the fluid on the solid, right. Let us say we have a kind of particle, right, and there is a kind of fluid coming in here like this. This fluid is approaching this particle. So, then there is a kind of depending on the flow conditions, streamlines may be developing like this. So, this particle whichever we have taken on this surface, on the surface of this particle may be experiencing some force because of the fluid, or the fluid is exerting some kind of force on the solid object surface. So, that force exerted by the fluid in the flow direction is known as the drag force. So, drag force is the force exerted by the fluid on the solid object, but in the flow direction. The direction should be flow direction, okay, that is important, direction of in the direction of flow, right. So, drag is the force in the direction of flow exerted by the fluid on the solid. And then we know by Newton's third law, an equal and opposite net force is exerted by the object on the fluid. So, whatever the drag force, let us say fluid is exerting a drag force of 10 newtons on a kind of solid object, then the solid object would be exerting a drag force or a equal and opposite force, that is minus 10 newtons force on the fluid. Okay. So, this drag has two components, one is the form drag or the pressure drag that we already know, and there is another one wall drag or shear drag or friction drag or viscous drag. There are several terms for this wall drag. So, it is having two components. So, the drag is having two components. Now, we see how to evaluate them. So, in order to know how to evaluate them, we have to take a geometry where both the components are existing. What does it mean by? There may be some conditions or some kind of flow geometries where maybe only one of the component, one of the drag component is dominating, other drag component may be negligible. Some cases there may be form drag is dominating compared to the wall drag, whereas in some other cases wall drag may be dominating over the form drag, so that the form drag can be negligible. However, since we are starting with to understand how to evaluate these drag forces, what we do? We start with a kind of object and which having both the components, okay, right. So, let us take a solid object where it is making an angle with the direction of flow. So, that is wall of immersed object will be taking which is making an angle with the direction of flow. Let us say we have this geometry, this is the geometry that we are having like this. Okay. So, probably it is let us say kind of spherical object or an object which is having some kind of curvature. Okay, we are taking only this portion, let us say. So, along this solid object surface, what you do, you take an element whose area is dA, right. So, now this object is fixed. So, the one fluid is coming, one Newtonian fluid is coming with velocity u naught, let us say, and then this is the direction of the flow, that is the horizontal direction flow is there, right. So, now rather on this element, on this entire object, this fluid when it comes and interacting, it is exerting some kind of a force, right. That force, if take its component in the flow direction, so that is the drag force, right. Okay. So, now but this element is making angle 90 minus alpha with the flow direction. Okay. Whereas, so if you have this dotted line in this direction here, so this angle would be the alpha. Now, on this element, it is having two components. One is the pressure component, another one is the wall shear component. Pressure component would be acting normal to the surface like this, right. So, normal to the surface of this element, whatever the force is there, that is due to the pressure, and then that force is P into dA. That force is nothing but P multiplied by the area of that object, that whatever we have seen. So, that is P dA. Similarly, this element is also having a kind of or experiencing a kind of shearing force. The shearing force would be in a kind of a direction parallel to the orientation of this object, whatever we have taken. So, that is this direction, right. So, shearing force is what? Shearing force is tau w multiplied by the area of that whatever the surface through which it is acting. So, that is tau w multiplied by dA, that is the shearing force. Now, what we understand, this pressure force on this element that we have taken, that is acting in this direction, right, towards the element's direction, whereas the shearing force whatever is there, that is working in this direction. So, but we need their components in the flow direction. What is drag? Drag is the kind of force exerted by the fluid on the solid object in the flow direction. So, now we have to find out their respective component in the flow direction, that is in the horizontal direction. So, now, so here if let us take this pressure force term, if this is the alpha angle, so then whatever this component is there, that should be P sin alpha dA, and then this component should be in the flow direction or horizontal, that should be P cos alpha dA. So, P cos alpha dA here, P cos alpha dA. So, the same is represented here in the above, so that to have enough clarity picture, right. So, this P cos alpha dA is going to be form drag or the pressure force or the force due to the pressure component whatever is there, its horizontal component, because the flow direction is horizontal now here, its horizontal component is P cos alpha dA. So, that is going to be form drag, and then similarly here tau w dA, this is in this direction. So, now what is this angle? This angle is nothing but 90 minus alpha. So, this is going to be tau w sin 90 minus alpha dA, and this is this particular component is going to be tau w cos 90 minus alpha dA. So, tau w sin alpha dA. So, whatever the shearing force there on this particular element, it is not in the horizontal direction. So, we have evaluated its component, vertical and horizontal component. Since the flow is in the horizontal direction, so shearing force component in the horizontal direction is tau w sin alpha dA. So, this is going to be wall drag. This is how we are going to evaluate these drag components for a given geometry. Remember, if the geometry orientation changes or entire geometry changes, let us say if you have a kind of a geometry like this, so then things may be very different, right. Let us say you have a kind of a geometry like this, then it is going to be different. Okay, geometry and then its orientation, if you have a kind of irregular particle like this. So, not only geometry, its orientation is also going to have a kind of influence, right. So, for a given geometry one has to evaluate what are their respective pressure and then viscous drag components, then one has to do the calculation accordingly. So, like this you can divide the surface into the n number of elements like this, right. For each element you find out what is this form drag and then what is the wall drag for each element, and then you add them together for each element and then you integrate all those quantities, then you will get the total drag for the entire surface, Remember these things we are taken, we derived P cos alpha dA and then tau w sin alpha dA or only for one single element having the area dA. So, area of the selected element here is dA, angle of inclination to the direction of flow is 90 minus alpha, and then component of the wall shear in the direction of the flow contributes to the drag. Similarly, another contribution causes from the fluid pressure which acts in the direction normal to the wall. Pressure actually acts normal to the wall, but the drag comes from the pressure component in the direction of flow. So, the corresponding flow direction component we have to find out, and then that should be taken as a kind of pressure drag. Total drag on an element of area is the sum of the two components whatever we have seen. So, now for this object that we have taken, wall drag that is coming from the wall shear is nothing but tau w sin alpha dA. Similarly, form drag that is coming from the pressure component, that is P cos alpha dA. So, the total drag on element of area dA is sum of these two quantities whatever tau w sin alpha dA and then P cos alpha dA. Similarly, total drag for the entire object surface, whatever the entire object surface we have taken. So, that should be the integral of total drag on each element of area dA. You have to divide the surface of the entire object into the small element, and then for each element you have to find out what is the wall drag, what is the form drag, then you have to add them together. Like that for individual elements you have to do, and then you integrate for the entire surface, then you will get the total drag for the entire solid object by integrating them. Okay. So, as I mentioned, if you have a kind of object like this, your expressions may be different. If you have a kind of object like this, your expressions may be different. If you have a kind of object like this, then again needle like object like this, irregular particles like this. So, all of them are going to evolve in different expression for this form drag and then wall drag. So, what I mean to say, whatever this wall drag or form drag expressions derived here, they are valid only for the object and then only for the orientation, the inclination angle that is shown in the previous slide. They are not unanimously true for all the objects. It is going to be different for a cube, it is going to be different for a cylinder, and then it is going to be different for a cylinder, one cylinder to the other cylinder of having different orientation to the flow direction. So that is how they are depending on a kind of case to case. Okay. Now we take a case where we can see that only one of these component may be dominating, other components may be negligible. Like, so let us take flow past a very thin flat plate, flow parallel with the plate, right. So then what happens? Now let us assume this is a thin flat plate that we are taking, this paper sheet, very thin, this is very thin, you can see like this, very thin. So now what you do, you can have a orientation in different directions. So let us say the flow is coming from your left to right. So then, and if you take this orientation, then drag would be different, and then if you make this orientation like this, it will be very different drag, and then if you make orientation like this and then flow is still left to right, so then the drag is going to different. So what we do, we take a kind of case, this flat but very thin plate like this, maybe like this, that we have taken, its orientation is that now the flow is coming from your left to right like this. So then here what happens, this surface is only offering the resistance that is normal to the surface. So that is pressure drag is going to be very small, whereas this entire surface is offering kind of a shearing force. When the fluid coming here and then flowing like this entire surface area is going to offer kind of some kind of force, or it is going to experience some kind of a shearing force while this fluid is flowing in this direction. So then what kind of drag is there? So since now the same pictorially if we have a kind of this object like this, thin plate like this, right. So now the fluid is coming from left to right with a kind of uniform velocity. The direction of flow is the left to right in the horizontal direction. So this object, now as I said, this is the flow direction. So this surface, whatever this surface is going to offer, or this surface, whatever the force that is being receiving because of the fluid flow, that is going to be very small, whereas the force that this surface is going to receive because of the fluid motion, that is going to be large. So this direction force whatever is there, that is the pressure component, and this surface whatever is there because of this one, whatever the drag component is there, that is the shearing drag. So shearing drag, wall drag is more important, more larger compared to the pressure drag here. So what we say here, in such kind of flow, when the fluid is coming without any distortion, it's smoothly going past like this. They are not deviating much from their streamline, from their this direction, flow direction. They are not much deviating, only near the surface slight deviation is there, and then after that it is going to be same like flow direction. So here what we have, only drag force here is wall shear per unit projected area of the thin plate. So only force that is exerted, or the whatever the fluid is exerting a force, that is majorly exerting a kind of shearing force on the surface, right. It is also exerting some amount of the form the pressure force, but that is very very small. So we can say only drag force in such kind of geometry is a kind of a wall shear drag. Now the same plate, if you rather keeping like this, what you do, you keep like this, orientation if you change, that is the flow perpendicular to plate. So the plate direction and then the orientation of the plate and flow direction are perpendicular to each other. So like this, so this entire surface is exerting kind of a receiving a kind of the drag force due to the pressure component, and then this surface, whatever this surface is there, the very thin surface, that is going to have a kind of shearing component. So now in this orientation, this pressure component, because of the more frontal area, so the resistance whatever there because of the pressure component, that is more compared to the resistance because of the shearing component. So under such conditions, the geometry if you take, so the same geometry like this, we have same geometry like this here. and then flow is coming in the same left to right direction in the horizontal direction. So, when it comes, it offers the form of the object. The form of the object is offering or receiving more force because of the fluid, and then since the object is offering some resistance to the fluid in the opposite direction. So, what happens, the fluid try to escape, has to jump over and then form a kind of a recirculation eddy, something like this. So, these are the recirculation eddies in general, right. So, they are forming like this. So, under these conditions, whatever the drag is there, that is primarily due to the pressure component only, that is form drag only, whereas the wall drag is a kind of very small component here. So, these are the two extremes for the case of the previous case where we have considered both the components are there. So, that is the reason when we are evaluating the expression for the form drag or the wall drag. So, we should be careful about the orientation of the geometry, flow direction, etc., and then accordingly we have to derive their expressions. We cannot use one single expression unanimously or universally for all kind of objects and all kind of geometries. It is not possible, right. So, the flow direction and then shape of the geometry, orientation of geometry are going to be having a kind of very important role in these drag components. That is, we can see the same plate, if the orientation is changing from one orientation to other orientation, in one orientation pressure component is dominating, so other orientation wall shear component is dominating. So, now how to define the drag coefficient, right. So, we know now this is the drag, how much important, how to evaluate these things. So, then we have to evaluate some kind of expression for the coefficient, drag coefficients, or something like non-dimensionalized drag, like friction factor we have seen. Like in flow through pipes or channels, etc., we have seen the friction factor. What is friction factor? Friction factor we have defined as a kind of a dimensionless wall shear stress, that is wall shear stress divided by the velocity head multiplied by this density, or if you non-dimensionalize this wall shear stress by velocity head and then density, then we get this friction factor, that is tau w by v square by 2 rho, or tau w by rho v square by 2. So, this is how we have defined the friction factor for flow through pipes and channels in general in our fluid mechanics course, right. Similar way, we can also define the drag coefficient. How to define the drag coefficient? We can similar way define the drag force per unit area, because now here in this drag coefficient case, it is not the only wall shear component, but the pressure component is also involved. So, when we add together, then we have the drag force. So, drag force divided by unit area, some kind of unit area, and that force, the drag force per unit area, if you normalize, non-dimensionalized with the same velocity head and density, then we get drag coefficient. So, what kind of area here we take? We take the projected area. We do not take a surface area, or we do not take a kind of cross sectional area kind of thing. We take a projected area. Why projected area? That is also we are going to see. So, that is analogously for immersed solid objects, it is the drag coefficient, and it is defined as CD is equals to drag force per unit area divided by the velocity head multiplied by density. So, FD by AP is similar, analogous to tau w whatever we have taken, not similar, analogous to the tau w whatever we have taken in friction factor, and then this of rho v square is a kind of velocity head and density components for the non-dimensionalized. So, this is how CD is defined. Drag coefficient is designated by CD, friction factor is designated by F, right. So, now we see the nomenclature, what is FD, what is AP, V, etc., that is what we are going to see now. FD is the total drag force, that is fluid is exerting on the solid object, and then AP is the projected area of the fluid, projected area we are going to see now, and then FD by AP is the average drag per unit area of the surface, and then V is the uniform velocity of the fluid or approaching velocity of the fluid, and rho is the density of the fluid. So, now projected area of the solid object, how to define it is? It is defined as the area obtained by projecting the object on a plane perpendicular to the direction of flow. So, that is how the projected area is defined, or it is also referred as the area of the particle that is seen by the approaching fluid. Okay. So, now pictorially we see some examples. Now, we take a projected area of a sphere, we try to calculate. So, we try to calculate now projected area for different objects. So, we take a kind of spherical object, let us say like this. Right. So, now from here the fluid element is coming, or the approaching fluid is coming from here in this direction, right. So, when this flow comes here, it is here, depending on the how small or large is the magnitude of this fluid, the velocity streamlines, the flow streamlines, we can have different shapes like this. Okay. So, now the projected area of this solid sphere, solid spherical particle, is the area that you can see from the flow direction. What you see now, let us say, assume this is a kind of spherical object, this is a spherical object, right. Let us assume this is a kind of spherical object. So, now this is from this direction the flow is coming. So, what you see now here, what you see a kind of circle only. So, the projected area for the sphere is nothing but the area of the circle, right, that can be seen. So, that area that we can see, like we can draw like something like this. So, now let us say size of this particle, spherical particle, is dp. So, whatever the circle that we see here, something like this. So, its area, what is the area of this circle, is pi r square, or pi dp square by 4. This is going to be projected area for a kind of spherical particle. That is how one has to obtain the projected area, or simply it is the area seen by the approaching fluid elements, right. So, for the sphere, the projected area is that of a circle, that is pi r square or pi dp square by 4, where dp is the diameter of the sphere. Now, what we do? We take a another case, projected area of a cylinder with its axis perpendicular to flow direction. So, let us this is now, you take it as a kind of a cylindrical particle. Now, this cylindrical particle, so in this direction the fluid is coming. So, from here, or let us assume you are from there you are seeing from on screen. So, I am seeing from here. So, what you see, which area you see? Area of this object, if you project on this surface plane. So, what you get? You will be getting the area of a rectangle column, right. So, that is height L multiplied by dp, diameter of the cylinder, whatever that area is there, that is the projected area of this cylinder. So, pictorially if you draw it here. So, now this is the cylinder, small cylinder that we have, cylindrical particle or even cylinder, whatever you call it. So, it is having length L and then diameter dp. So, now here the flow is coming here in this direction like this, right. Again here also, depending on the flow, depending on the magnitude of the velocity, approaching velocity. So, there may be kind of some kind of recirculation wakes, something like this, or there may not be any recirculation wakes if the flow is very small. So, something like this, the streamlines you can see. Now, what should be the projected area? Or from here, when you are seeing it, you are seeing it as a kind of a rectangle. You are when you are projecting on a plane in the flow direction. So, you see it is a kind of rectangular of size L and dp. So, what should be the projected area for cylinder with its axis perpendicular to flow direction? It should be the L multiplied by dP. Okay. Similarly, if you take projected area of a cylinder with its axis, so the central axis, this is the central axis now, it is parallel to the flow direction like this. So, that is now the flow is coming from this side to this side like this, right. So, then from your screen side you can see now. So, what is the area that you are going to see of this cylinder when you project it on the plane in the flow direction? When you project it on a plane in the flow direction, then what you see, you can here also you can see a kind of circle, you can see a kind of circle. So, for this geometry also the projected area is the area of this circle that you are going to see. So, that is, let us say you have a cylinder like this. Okay. So, right, now these fluid elements are coming like this here. So, depending on the flow, again here also there may be vertices, there may not be any vertices, the streamlines may be something like this. But from the flow direction, from the direction of the flow, what you see only a kind of a circle, you see only a kind of circle, right, whose diameter is same as the diameter of the cylinder. So, that is dP. What is the area of the circle is again pi dP square by 4. So, here also the projected area is pi dP square by 4. So, this is how one has to discuss about this projected area. Now, let us say if you take a cube of equal size, let us say you have a cube like this. Two-dimensional cube I am drawing here. So, if you draw three-dimensional, something like this. So, now the size is L, it is a equal size cube. So, all sizes are equal to L. So, now the fluid is coming something like this here and then going like this. So, when it comes, depending on the flow conditions, the streamlines will take form after the geometry like this. So, but now here again if you see from the fluid side, if you see from the fluid side, if you see what you see here, you see a kind of square of shape L. So, what should be the projected area for cube of equal size L, then that should be the area of fluid facing square, that is L square. So, this is about the projected area, and this projected area is different from the surface area or cross section area. One should not be confused. So, in obtaining the drag coefficient, the drag force is divided by the projected area of the object. Okay. So, now we take for spherical particles. For simplicity, let us start with the spherical particles. Why? Because spherical particle is having the size equal dP, the size of the particle is same in all orientations or any direction. Theta is equals to 0 to 360 and pi is equals to 0 to 360, any direction if you see, it is having a kind of uniform size dP. So, that is the reason of simplicity that we case, for the simplicity we take this spherical particle case. So, what we have parameters in general, let us say for the spherical particles, it is settling in a kind of Newtonian fluid, or along this particle there is a kind of Newtonian fluid is flowing like this. So, what are the parameters are involved? One is the diameter of the particle, then the density and viscosity of the fluid, then the velocity of the fluid that is approaching the sphere, and then the force that is exerted by the fluid on the solid surface of the sphere in the flow direction, that is drag force. So, its non-dimensionalized quantity is a drag coefficient. Okay. Fd is the drag force, that is the dimensional quantity, Cd is the dimensionless quantity, that is the drag coefficient, right. So, these are the parameters involved. There may be other parameters, the surface roughness, etc., all those kind of things. These are the primarily that we see, okay, smooth sphere like that. Then if you do dimensional consideration or dimensional analysis, if you do, then what you can find two dimensionless parameters you can see here. The one is the drag coefficient, a function of Reynolds number. Drag coefficient and Reynolds number are the two dimensionless parameters that we can see here, and then what we understand from this dimensional analysis, the CD is going to be function of Reynolds number, REP, right. So, for REP for a particle in a fluid is defined as dP V rho by mu, that is dV rho by mu, or dP V rho by mu is the Reynolds number for a particle settling in a kind of Newtonian fluid. So, this Reynolds number is a kind of a ratio between the inertial forces to the viscous forces. It indicates the degree of these contributions. Like if the Reynolds number is small, then we can say that the viscous force is more dominating compared to the inertial force, so that inertial forces may be neglected and then only viscous forces may be considered for the analysis if the Reynolds number is very small, less than 0.1 or less than 0.01, something like that. If the Reynolds number is very large, order of 10 power 3 or 10 power 5, something like that, then we can say the inertial forces are more dominating compared to the viscous forces. So, one can avoid the viscous forces and then consider only inertial forces for their analysis. That is going to be, that is how rational way of using this Reynolds number. Okay. For this object, it is going to be dP V rho by mu. If all dimensions of object are not equal as in the case of sphere, then drag coefficient may be dependent on the shape factor and orientation of the object as well. So, as I already mentioned, in this drag coefficient, the orientation of the object, shape of the object is also going to have a kind of different role. The same thin plate, if orientation is changing, the drag component is entirely changing from horizontal to the vertical direction orientation. If you make, the components are entirely changing, their contributions are entirely becoming opposite to each other, right. So, that is different CD versus REP relations exist for each shape and orientation of a particle. Okay. Only for the spherical particle there is only one kind of correlation, but otherwise or one kind of CD versus REP relation. Whereas for the other objects, cylinders, cubes, etc., depending on the orientation, you will get the different CD versus REP relations. For spherical particles settling in a Newtonian fluid, that is at small Reynolds number, very small Reynolds number, less than 0.1, the drag force is evaluated as 3 pi mu v dP, that is known as the Stokes law, right. So, in the momentum equation, what you can do, the Reynolds number is very small. So, you can strike out all the inertial forces terms and then simplify the momentum equation. So, then you get the velocity profile, and then from the velocity profile you obtain the forces acting on the surface, and then pressure forces, and then viscous forces on the surface. There you take their component in the flow direction, add them together. So, then you will get the drag force. So, that drag force is 3 pi mu v dP. We are not going to do the derivation, that derivation usually comes into transport phenomena course part. Okay. So, if Reynolds number is small, for spherical particle, drag force Fd is equals to 3 pi mu v dP. It is also known as the Stokes law. If you non-dimensionalize this one, that is, if you do Fd by Ap divided by half rho v square, then you will get the CD, drag coefficient, non-dimensionalized quantity. So, Fd is 3 pi mu v dP divided by 0.5 rho v square. What is Ap? Pi dP square by 4. Projected area for a sphere is the area of the circle that you can see from the approaching fluid side. So, that is pi dP square by 4. So, then when you simplify, you will get 24 mu by rho v dP, that is 24 by REP. So, some of you may also be knowing as for spherical particles settling in a Newtonian fluid, Stokes law is nothing but CD is equals to 24 by REP. So, that is coming from this one. At such low REP, the terminal velocity of a spherical particle is given as g dp square delta rho, that is rho p minus rho divided by 18 mu. We are going to derive these relations in the next class anyway. Okay. So, what we understand here, if the Reynolds number is small, the settling velocity or the terminal velocity of the particle v is proportional to dp square, a square of the particle size. So, this above FD or CD is valid only when REP is very smaller than 1, that is 1 or less than 0.1, then only it is valid. It is known as, this type of flow is also called as the creeping flow or Stokes flow or viscous flow, it is known as. So, the streamlines, let us say, they will be occurring like this. If you, this is your solid object or spherical particle, and then let us say flow is coming from this direction like this. So, there will be a kind of 4.5 symmetry we can see here. So, that is whatever the, now if you break this, cut this surface like this. So, whatever the streamlines you see in the left hand side, the same streamline, same path line, etc., that you can, streamlines you can see is similarly exactly same mirror images of each other, right. Also, if you cut off in this direction, in the horizontal direction, so then whatever the streamlines at the top are there, so they will be exactly at the bottom also without any kind of deviation. So, that is the symmetric in either of the direction, left and right, that is fore and aft, and top and bottom symmetry of the streamlines we can see. So, that is the particles are, simply they are coming and then climbing, creeping slowly like this, and then falling down slowly without being affected by the presence of these particles. So, that is how the streamlines look for the creeping flow conditions. Further, wall shear is the result of viscous forces only here, because inertial forces are almost negligible. For such small Reynolds number, inertial forces are almost negligible. This law is valid for calculating the resistance of small particles such as dust or fogs moving through gases or low viscosity fluids. Under such conditions only, when you have the particles very small as well as the viscosity is also very small, then it happens in general the Reynolds number is going to be very small. So, you have this REP is going to be very small. If you evaluate drag coefficient, that CD is equals to 24 by RE whatever is there. Here you can see 1/3 of the CD is contributing in CDP is contributing 1/3 of the CD, and then CDF, that is the friction drag or wall drag, that is contributing 2/3 of the total drag coefficient. Okay. So, that is at the small Reynolds number under the Stokes flow conditions. Now, what happens if the Reynolds number slowly increases? Reynolds number slowly increases, let us say you go up to Reynolds number 20, something like this. So, that is the flow velocity is increasing. Now, the velocity of this fluid is increased when it is flowing past a spherical particle. So, what happens, these streamlines slowly climb up, and then now here the more they are receiving more resistance because the velocity is increased. So, because of that one, there will be a kind of vortices forming in this rear end of the particle like this. So, there will be vortices forming like this, and then these vortices are exactly same both in the top and bottom of, that is the axisymmetrically we can see any angle that you cut, above whatever the streamlines are there, exactly below the streamlines will also be the exactly same, or the recirculation Vx would be exactly the same, right. If you further go increase the Reynolds number, what happens? This size of this vertex increases, right, the gradually increases, but still this symmetry, you can see that symmetry, that is whatever the above the this dotted lines and this axis whatever you take. So, whatever the streamlines are there or the vertex shapes are there, exactly the same vertex shapes you can see and in the bottom of that one, that is known as the axis symmetry of the flow pattern. But if you further increase the Reynolds number, keep on increasing the Reynolds number, let us say if you go beyond 270 or 250 something like this, then what happens, these streamlines, the vertex further may increase something like this, but their shapes are not same. So, here that is in one case this, let us say here bottom vertex shape is this much, and then top vertex here that shape is like this. They are not symmetric each other. Here they are exactly symmetric, ending at the same point here. Here also ending at the same point here. Now the top one is ending at this point here, whereas the bottom one is ending at this point here. So they are not same here. And then sometime if you further increase the Reynolds number, what happens, these vertex may be breaking, and then a kind of non-periodic or periodic vertices are maybe forming like this. Okay. So this is how the flow pattern looks like for the kind of flow path sphere in general. So these are a very few minimum information that is required to be given at UG level. There are much more physics involved, and then reasoning and all those things are involved. So that is not going to be main part of this course anyway. So we are not going into this more details. We are studying only this to see which is the limit for the constant drag relations, etc. Those kind of we are going to see. So vortexes in this in the recirculating wake dissipate considerable mechanical energy and cause the pressure to be much less than the upstream pressure. So when these vortex are forming, the pressure in the vortex side would be much lesser than the upstream pressures. This makes the form drag quite large relative to the drag caused by the wall shear. Let us say at REP is equals to 0.1, CD is what, is nothing but 24 by 0.1 is 240. So here CDP is 1/3 of this one is approximately 80, CDF is approximately 2/3 of this one, that is 160. Whereas here when REP is 100, CD is approximately 1.1, and then pressure force is almost 0.6, friction drag is 0.5. So gradually what happens, what you can see, at small Reynolds number, pressure component is only 1/3. As Reynolds number is increasing, let us say up to RE 100 is almost 50-50, even more than 55 to 60% is pressure component. It increased from at low Reynolds number it is only 1/3, now it is increased almost up to 55 to 60%. If you further go to the higher and higher Reynolds number, what you can see pressure component is the one quite large compared to the wall drag or the friction component. Okay. For REP in the order of 10 power 3 to 10 power 5, CD is nearly constant between 0.4 to 0.45, that slightly changing as the point of boundary layer separation slowly shifts towards the nose of the sphere, towards the nose top of the sphere. So this region where this drag coefficient becomes constant 0.4 to 0.45 is known as the Newton's law, that is constant CD value. And then under these conditions also, if you derive the terminal velocity, then you can find it that V is proportional to dp power 0.5. Under the small Reynolds number cases, what we have seen, V terminal velocity is proportional to dp square. Under the large Reynolds number conditions, what we have seen here, V is proportional to dp power 0.5. For non-spherical particles, it is necessary to specify the size and geometric form of the object and its orientation with respect to the direction of flow of fluid. For such particles objects, one major dimension is chosen as the characteristic length, and the other important dimensions are given as ratios to the chosen one. For instance, for circular cylinder, the diameter is taken as the defining dimension and the length is expressed as the L by D ratio. These are the in general conventions. Now let us say if you take the drag coefficient versus Reynolds number REP or NREP, either way it represented. Now you can see the solid line that is for the spherical particles, and then Disc also it is shown, and then cylinders also it is shown here. So, disc and then spherical particles are having almost similar drag behavior up to Re 100 or so. The drag coefficient for spheres and disc are almost same, but after that you can see deviation is very much higher. Whereas compared to the cylinders, the deviation between drag coefficient of cylinder and disc or cylinder or sphere is very much higher up to Reynolds number, but after this again the difference between sphere and cylinder drag coefficient is very much higher, but for disc and cylinders they are almost similar to each other. So, like this, these drag correlations are available either in the I mean like a graphical form like this, or in a kind of a correlation forms for a standard kind of objects like spheres, cylinders, etc., discs, etc., or one can obtain by a numerical analysis or the experimental results anyway one can obtain them. So, the references, the majority of the information, indeed almost all information presented in this lecture has been taken from this reference book, McCabe Smith and Harriot, Unit Operations of Chemical Engineering. There are also reference books in our courses. One can go through this Unit Operations of Particulate Solids Theory and Practice by Ortega Rivas. Then Carlson and Richardson's Chemical Engineering, second volume by Richardson and Harker. Then Transport Processes and Unit Operations by Giancopoulos. Then Unit Operations by Brown et al. And then Introduction to Chemical Engineering by Badger and Banchero. Thank you.